Students are requested to drop down their names for attendance purpose. We will be starting in a while. Students are requested to drop down their name for attendance purpose. We will be starting in a while. Good evening. Okay, good. So, I think all of you are there now. Good. So, we will be starting now. See, first we will just quickly have an overview, right? That what we have learned basically. So, discovery of fundamental particles we are already done. Proton, neutron, electron, atomic models we have completed. Thomson's model, Rutherford's model, Bohr's model, and then we will discuss about the quantum mechanical model in the next session. Spectral studies we have already discussed. Photoelectric effect we have discussed, and today we will deal about the uncertainty principle as well as the dual behavior of matter. Okay. So, here if you see that if you take photoelectric effect, let us say, we are taking what? Photoelectric effects. So, what does photoelectric effect tell us? Photoelectric effect tells us that basically the electromagnetic radiation, that is light basically, was having a particle nature, right? It was having a particle nature, right? This means that particle nature of wave can be explained by the photoelectric effect, which we had studied in the previous session, that the radiations or the light can travel in is basically made up of what? Photons, right? That which is having, each particle is having a energy of h nu. So this depicted that how a particular wave can be present in the particle form. So particle nature of light we have already done with. Now this photoelectric effect was also explained by the or sorry, accompanied by the Compton effect, right? Compton effect also explained that there is a particle nature of electromagnetic radiations. Okay, so yes, it is the Heisenberg uncertainty principle, Ju. Yeah, Arun, you can take your doubts after the class. Okay, so in Compton effect, the scientists found out that basically the X-rays, which we were discussing in the previous sessions, basically that it is also a electromagnetic radiation, was also found to have a particle nature. That means that electromagnetic radiations can be present in the waveform as well as in the particle form. Now, the question arises that if electromagnetic radiation, which was previously known as a wave basically, is having a particle nature, then why can't particles have a wave nature? Then why can't particles have a wave nature? Right? So, from there we discovered the wave nature of matter. We said that each matter is consisting of the dual nature. What is dual nature? Basically wave nature as well as the particle nature, right? So, I think you must be clear that how the idea of treating matter as a wave or basically the dual nature of matter can be idealized out, right? Because if electromagnetic radiations, which were previously known as wave, can behave as particles, why can't the particles have a wave nature, right? So first we will discuss about the de Broglie theory or the de Broglie, okay? Because certain people in American accent, basically they pronounce it as de Broglie, right? So de Broglie theory or de Broglie theory. So if you consider the key concept of de Broglie theory, he said that the matter will be having wave nature as well as the particle nature, right? So we are already knowing that matter is having a particle nature, right? Because in the Bohr's model also he considered that the electrons are subatomic particles, they have a particle nature, right? So de Broglie theory said no, if electromagnetic radiation can basically have a particle nature, then why can't matter have a wave nature itself, right? So this was the key concept behind the de Broglie theory, right? So he considered that each matter, right, whether it is a small particle or whether it is a big particle, for example, the smaller particles, let us say electrons, the bigger particles, let us say football, right? So they both are associated with the particle nature also and the wave nature also. So if you consider the particle nature of matter, energy will be given as mc square, which was proposed by Einstein, right? And this was proposed by Planck, that E equals to h nu, that is the small packets of energy basically, right? So what we do is that de Broglie equated the two, because in this, if you see, this is the classical model in which E equals to mc square was given by Einstein, right? And this equation was given by Planck. So he equated the two energies, and what he found that mc square equals to h c by lambda, because nu is the frequency which is given by c by lambda, where c is the speed and lambda is the wavelength, right? So now c and c gets cancelled. What we are left with, that mc equals to what? H by lambda, or rearranging we can get it as lambda equals to h by mc, right? Now we know that momentum for any particle or momentum is given as basically what? The linear momentum I am talking about. So linear momentum is having a formula of what? Mass into velocity, right? And the linear momentum is symbolized by T. So lambda will be equals to h by p, right? So he stated that each matter, whether it be a smaller particle or the bigger particle, if you say, all are associated with a wave, right? Now, these kind of waves are known as matter waves. These kind of waves which are associated with the matter are known as matter waves, because he considered that now for matter, particle nature is also there and wave nature is also there, right? So he said that the waves which are associated with the matter are known as matter waves. Okay, am I clear? Is the de Broglie theory clear? You can just give a thumbs up in the chat section box and let me know. The formula that was given by de Broglie was basically what? Lambda equals to h by p, where p is what? The momentum, h is what? The Planck's constant, and lambda is what? The wavelength of the lambda is of what? Lambda is of the wavelength of the matter waves, right? Lambda is basically the wavelength of the matter waves which are associated with each matter. We will study the property of matter waves in the coming slides. Good. Has everyone understood? So linear momentum, we already know that it is given by what? Mass into velocity. Okay. So de Broglie theory, if it comes to write down that what is the basically de Broglie theory, it is that each matter is associated with matter waves and there is a dual nature of matter, right? That is the particle nature also and the wave nature also, right? So he basically equated mc square equals to h nu, and then he arrived to the formula that lambda equals to h by p, where h is the Planck's constant and p is the linear momentum, which is also given as mass into velocity. Now the question arises that if he is saying, let us say that the particles as smaller as electron and the particle as bigger as the football both are associated with waves, then why can't we see waves associated with the football, right? Why the waves or the matter waves which are associated with the football cannot be seen? So the answer lies in his equation that he proposed. We saw that lambda equals to h by p basically, right? Where p is the momentum and it can be given as mv. So for a football, if you see, the mass is much higher. For electron, if you see, let us say the football is of 2 kg, right? Let us say football is of 2000 grams. So on the other hand, if you see mass of the electron, it is very, very, very smaller than that of the mass of the football, right? Approximately 10 raised to the power minus 31 kg. So what happens here is that mass of the football tends to be more bigger, right? As lambda and m are inversely proportional. So what do you see? That if we increase on m, that is in case of football, if you see the mass is very much greater, so what will happen to lambda? Lambda will be very, very, very short to be observed. That is why with bigger particles we cannot observe the matter waves. Okay, while in the case of smaller particles like electron, protons, right, the subatomic particles basically which have a very small mass, especially the electron, right. So there the waves can be observed because the wavelength will be greater. So lesser mass, more wavelength, more mass, lesser wavelength, right. So because of the short wavelength and due to the greater mass of football and other particles which are bigger, we cannot see the wave matter waves, right, associated with that particular matter. So next was the de Broglie wavelength formula that we have also already done, that lambda equals to what? H by p, where lambda is the wavelength and h is the Planck's constant and p is what? The basic momentum, or you can also write it as h by mv. H by mv, where m is the mass of the object, v is the velocity, lambda is the wavelength of the matter wave that is associated with that particular matter, and h is the Planck's constant. Now, the key concept of matter waves, this is important, that what are basically matter waves, right? Matter wave represents the probability of finding a particle in space. For example, let us say that if you consider a particle, right, I am saying that a particle is present here. That means I can 100% tell that the particle's position is here, right? But if I represent the particle in a wave form, I cannot 100% say that the particle is present in which position. Rather, we talk about the probability of finding the particle in this region. Particle can be here also, 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 right? So the probability concept was extended in the quantum mechanical model. For the time being, you can say that if you consider the particle nature, we can say that 100% the particle is present here, right? But if you talk about the wave nature of the matter, if you are considering the wave nature of the matter, you cannot specify that where the electron is certainly present. Rather, you can just represent the probability of finding that particle in space. Okay. Next comes is the very important one, that is matter waves are not electromagnetic in nature. That means matter waves are not electromagnetic radiations. They are not associated with electrical component and the magnetic component, right? Third point is that de Broglie or matter wave is independent of the charge on the material particle, whether it be a proton, whether it be a neutron, whether it be an electron. The de Broglie or the matter wave is independent of the charge. It means that matter wave or the de Broglie wave is basically associated with every moving particle, whether it is charged or whether it is uncharged, right? So for neutron, if you see they are uncharged, there will be matter wave associated with it. If you see electron, it is charged, proton, it is charged. So there also you can see the matter wave associated with them. Okay. Next is the practical observation of matter waves is only possible when the de Broglie wavelength is of the order of size of the particles. So this states that basically the lambda that you are getting should be comparable with the mass of the matter. Then only you can see the practical observation of matter waves. We have already seen that you increase the mass much, then what will happen? That lambda will be too short to be observed practically. Okay. So these points are very important. These basically define that what are basically matter waves and what is the significance of matter waves. Okay. Now comes the de Broglie wavelength alternative formula. This is very important. See here that lambda equals to what? H by p, that we have done, where p is the momentum, h is the Planck's constant. Then p equals to, that is linear momentum, is equal to basically mass into velocity. So we can write p equals to mv. Now if you see the formula for kinetic energy, it will be what? Half mv square, right? If you multiply this by m and this by m, what you will get? Half m square v square divided by m equals to kinetic energy, right? Now, if you want to find out the value of m square v square, what will be this? M square v square equals to 2m into kinetic energy, which we are representing here as k only, right? So, or if you write mv, it will be what? Root of 2mk, right? Now we know that lambda was equal to what? H by mv. So lambda will be equal to what? H upon root of 2mk, where h is the Planck's constant, m is the mass of the particle, and k is the kinetic energy of particle. I hope I am clear. Is it clear, guys? Is it clear that how we can write lambda equals to h upon root 2 mk? We will be solving some questions, so pay attention to these formulas and learn these formula by heart because they have a frequent appearance in examinations. Okay. So next we will consider the formula h by root of 2qvm, right? Now how do we get this particular thing? See, kinetic energy, if you see, it is what basically half mv square, right? So you can write it down as half of m square v square, because they were not having the electrical component and the magnetic component in them, right? The properties which were shown by the electromagnetic radiations were not shown by the matter waves. And rest, that what are the properties of basically matter waves, what are stationary waves, what are electromagnetic wave, what is longitudinal, what is transverse wave, that you will learn in the physics, that is waves and oscillations chapter. So you will get a clear picture of that in that chapter. Okay. So kinetic energy becomes what? M square V square divided by 2m, right? Because we are multiplying m both the sides. So kinetic energy will be equal to half m square V square divided by m. So kinetic energy equals to what? P square by 2m. Can I write it like this? Because mv equals to p. So m square V square will be equal to p square. Am I correct? Now, kinetic energy, if you represent it in electron volt, see, what are the units of energy basically? Joule and electron volt, right? So, if you consider kinetic energy to be in electron volts, you will get P square divided by 2m, right? Or you can also write it as P square equals to 2m EV or 2m QV, where E represents the charge, m represents the mass, and V is not the velocity, it is the potential. It is the potential. It is not the velocity, this is the potential. So this becomes what? P square P equals to root 2 MeV, because P square was equal to what? 2 MeV, where V is the potential, E is the charge, M is the mass. So P can be written as root 2 MeV. So instead of P, I would write down what? Root of 2 MeV or QV. You can depict charge as Q also or E also, whatever you wish. Okay. So E is the charge or Q is the charge. So the final formula for de Broglie wavelength is what basically? It is lambda equals to h by p equals to h by mv equals to h upon root 2 km and equals to h upon root 2 qvm. Okay. Now here comes the question. If the Planck's constant is 6.6 into 10 raised to the power minus 34 joules second and the de Broglie wavelength of a particle having momentum of 3.3 into 10 raised to the power minus 24 meter per second, what will be the wavelength? They are asking about the wavelength. What is the de Broglie wavelength? Apply the formula and let me know the answer. Okay, Arun and Jude Allen has given the answer. What about others? Okay, Jainuram is also saying C. Dipashri? Anirudh is also saying, Acha, Anirudh is saying B. Okay, he's saying 2 angstrom. Okay, C. Okay, so let us see what is the answer. You have to find out the wavelength, h, and momentum is given basically. So the formula is very simple, h by p. So you will get 6.62 or 6.6 into 10 raised to the power minus 34 joules second, and 3.3 into 10 raised to the power minus 24 meter second. So second and second will get cancelled here. So 6.6 and 3.3 if you cancel, your answer will be 2 into this will be 10 raised to the power minus 34 plus 24, that will be equal to 10 raised to the power minus 10. So this will be in what? Meter. This will be in what? Meter. So what will happen now, that if it is in meter, we have to convert it into angstrom, right? So we know that 1 angstrom equals to 10 raised to the power minus 10 meter. So this 10 raised to the power minus 10 meter, you can write it as angstrom, and the answer will be 2 angstrom. So you all are correct with your answer, that is 2 angstrom. Good. Now do question number 2. The de Broglie wavelength of an electron accelerated by an electric field of V volts is given by. It is saying the de Broglie wavelength of an electron accelerated by an electric field of V volts is given by. So we know that H upon 2 MeV. So here we are taking what? Electron, right? So you have to put the mass of electron and the charge of electron and find out the relationship between lambda and root V. Find out the relationship between lambda and root V. Put the values of mass of electron and charge of electron in this formula, and also the value of Planck's constant. Put the value of M. Okay, Jude Allen is saying C. Let's see what other peoples are getting. Yes, you all are correct with your answer. The answer is C. If you put the mass of electron 9.1 into 10 raised to the power minus 31 kg, what is the charge on electron? 1.6 into 10 raised to the power minus 19 coulomb, and H value as 6.62 into 10 raised to the power minus 34 joules second, then you will obtain lambda as 1.23 divided by root V nanometer. This formula you have to remember it by heart, and it is only true for electron, because here we were keeping the mass of electron and the charge of electron. So this formula is only valid for electrons, right? So this you have to keep in mind. You can solve the questions in which basically potential is given for an electron, and then you can find out the de Broglie wavelength. So you can directly use this particular formula, right? This is a shortcut formula for the relationship between the potential and the lambda of the matter wave associated with the electron. Don't do the mistake of using this particular formula for protons or neutrons, okay, or other particles. Next, question number 3. Question number 3. You have to find out the ratio. Find out the ratio. Lithium 3 plus and a proton are accelerated by the same potential. That means V is same basically. And de Broglie wavelengths lambda Li and lambda P have the ratio what? So you have to find out lambda Li divided by lambda of for proton ratio. Consider that mass of lithium is 9 times the mass of proton. Consider mass of lithium is 9 times the mass of proton. Yeah, also remember the previous formula that I told you to learn it by heart. The unit is in nanometer. You also have to remember this, right? The answer for lambda that you will be having by putting the potential will be in nanometer, right? So remember the unit itself, right? If the lambda is basically asked in meter, then what you will do, first you will find out in nanometer through this shortcut formula, and then you can convert it into meter itself. Now do this question and let me know the answer. Okay, Jude Allen is saying A. What about others? You can take the relative charge also, right? For example, if the proton is having a charge +1, because you are finding out the ratio, you can take the relative charge. If you are not finding out the ratio, then you have to take the actual charge, that is 1.6 into 10 raised to the power minus 19 coulomb, right? So for proton, it is +1, let us say. So lithium will be of +3. So you can put the relative charges value of proton and lithium as 1 and 3, and mass relationship is already given. So you have to find out lambda lithium divided by lambda associated with proton. Solve it and let me know what should be the answer. Solve it and let me know, guys, what should be the answer. Okay. So everyone is saying A. Dipashri, what is your answer? Okay, so Arun, Jainuram, Jude Allen. Okay. So here if you see that lambda was equal to what? Lambda of proton will be equal to what? H upon root 2 MeV. Similarly, lambda for lithium 3 plus will be what? H upon root 2 MeV. These are the formulas. Now we know that H will be same for proton also and for lithium also, right? So here if you consider the mass, we are knowing that mass of the proton, if we take it as mp, and charge if we take it as +1, and v we are keeping as it is, then for lithium 3 plus if you say 2 into what is the mass of lithium here, 9 into mass of proton, so you can write it here as 9 into mp. Then what is the charge on lithium? That is +3, so you can write down 3 here, and then v here, because it is saying by the same potential, so v and v will be the same. Now what you have to do, you have to calculate lambda Li upon lambda P. So lambda Li will be equal to H upon root 2 into 9 into mp into 3 into v divided by lambda of P, that will be H upon root 2 into mp into 1 into v. Now H and H will get cancelled, this will move to the numerator. So what are you left with? Mass of proton into 1 into v divided by 2 into 9 of mass of proton into 3 into v. So now what will happen? V and v will get cancelled, root v, root mp will get cancelled, root 2 and root 2 will get cancelled. You are just left with 1 upon root 9 into root 3. So that will be equal to what? Root 9 we are knowing it as 3. So this will be 1 upon 3 root 3. So this is how you can get this particular answer. So all of you that who have given the answer as A are very much correct. The answer for this particular question is A. Is it clear? Good. Now, next we will move on to, see here, de Broglie theory of matter waves, Bohr's model correlation. Now, in this topic, we will see that how de Broglie, correlated with the Bohr's model, right? So, in Bohr's model, if you see, Bohr was only considering the particle nature of electron. Bohr was only considering the particle nature of electron, while de Broglie said that the electron with the particle nature, it is also having a wave nature. It is also associated with a wave which is known as what? Matter waves. Now, the question is that what is the basic structure or nature of that matter wave, right? So, he said that generally if you take a wave, they are moving like this, right? They are continuously moving like this. But he said that the matter waves which are associated with electrons are not moving like this. They are stationary waves. They are stationary waves, or they are also known as what? Standing waves. They are also known as what? Standing waves. Stationary waves, or basically standing waves, right? They will just be present as it is. For example, let us say that this is the orbit in which electron is revolving. So the wave can be drawn like this. This is the Bohr orbit in which electron is revolving. So he said that the the matter wave which is associated with the electron is moving like this, right? It is stationary, it is not moving, it is stationary like this, the matter wave which is associated with electron, and it is not moving like the ordinary wave. Can you see here that crest and trough are alternately moving, right? Let us say that the ocean waves, if you take, what happens is that they are moving like this, right? The crest and trough are moving forward like this. But in case of stationary and standing waves, if you see, these waves, these crest and troughs do not move in space, right? That is why these kind of waves are known as stationary waves or standing waves. And these waves, that is the longitudinal wave, standing wave, you will elaborate this particular theory about these kind of waves in the waves and oscillations chapter itself. For the time being, you can know that these waves that are matter waves which are associated with the electron, as per D. Broglie, he said that these are not moving waves, these are stationary or the standing waves, right? So basically, what is the correlation? He said that, let us say that this is a nucleus according to Bohr, and according to Bohr, the electron is moving in definite orbits. The electron is moving in definite orbits that we studied at was n equals to 1, n equals to 2, n equals to 3. We have already done that. So De Broglie said that, let us say that the electron is present here, right? So this electron will revolve in this orbit, that is the second orbit, let us say, right? So here we can draw the matter wave associated with that electron like this. We can draw a matter wave of this associated with this electron particularly, which is moving in a certain orbit like this. Also, he found out a relation that 2 pi r equals to n lambda. Now, what does this mean? This means that the circumference of the orbit, you know, we have in Bohr's model, we have calculated the distance at which the electron is present, basically the radius of the orbit, right? Do you remember the formula? 0.529 angstrom, that one that we have discussed. So Bohr was able to tell the radius of that orbit, right? So he said that the circumference of this orbit, what is the circumference of the orbit as it is circular in nature? It will be equal to 2 pi r, is an integral multiple of the wavelength associated with the matter wave, right? I'll repeat again that the circumference of the orbit is an integral multiple of lambda of the wavelength of the matter wave associated with the electron, right? Now one thing is very interesting here. See, for example, let us say that 2 pi r equals to for orbit number 1, n equals to 1, so 2 pi r equals to lambda, right? For orbit number 2, this will be 2 pi r equals to 2 lambda. I am not cancelling 2 and 2. We will just explain that something out of this. First, let me make the observations and then we will come up to the conclusion. So this will be 2 pi r equals to 3 lambda, right? This means n equals to 1 will mean that the circumference of the orbit, it is only having one wavelength, right? What do you mean by one wavelength? See here, for example, you are considering this type of wave. So how do you determine lambda of that particular wave? The distance between two consecutive crest or two consecutive trough is known as what? Wavelength, right? So in n equals to 1, if you say, there will be only one crest and one trough, right? So the matter wave which will be associated with it will be somewhat like this, right? For n equals to 2, if you say, there are 2 lambdas in the whole orbit, right? That means what? That there are 2 wavelengths, that is 2 crest and 2 troughs. So how can you deal with that? One crest one valley, one crest, one valley, somewhat like this, right? So it will have, can you see that it is made up of two crests, right? So 2 lambda, right? So here if you see next, if you are considering 3 lambda, let us say, so it will have what? 3 wavelengths, that means one crest, yeah, so it will consist of 1, 2, 3, 4 crest, right? So this 2 pi r can be made like this, 1, 2, 4, 1, 2, 3, 4, right? So the matter wave will be somewhat like this, right? Are you able to see? Are you able to understand this particular thing? This you will not find in any book, right? These things are only mentioned in some standard books. Is it clear with you all? Is it clear with everyone? That what is the meaning of that formula that was given by de Broglie? That is 2 pi r equals to n lambda. That means the circumference for n equals to 1, the circumference will be made up of only 1 lambda. Okay. For n equals to 2, it will be 2 lambda. For n equals to 3, it will be 3 lambda. Okay. So now we will study that how de Broglie was able to explain the second postulate of Bohr's model, right? What was the second postulate of Bohr's model? That angular momentum, if you see, of an object, it is the integral multiple of h by 2 pi, right? Or we can write it down as angular momentum is what? Basically linear momentum into the length, right? So mvr equals to nh divided by 2 pi. This was the second postulate of Bohr's. Okay. Now if you see, the formula that was given by Bohr's was, de Broglie was what? That 2 pi r is equal to what? N lambda, right? Now we know that 2 pi r equals to, lambda was what? Basically h by p, right? Or lambda was equal to what? H by mv, because linear momentum is given by mass into velocity. So this will be what? N into h upon mv. Now this becomes what? mvr equals to nh by 2 pi. What I have done? I have just keep that mv in the this side on the left hand side and 2 pi on the denominator side of the right hand side, right? So this was the formula that was given randomly by Bohr, right? Bohr only said that mvr equals to nh2 by, and could not explain the practical significance basically, right? So de Broglie explained the practical significance, or how that particular formula can be derived, right? So this is how the de Broglie theory of matter waves was correlated with Bohr's model. Okay. Now next we will study, here if you study, see, if I am drawing this wave, what is n here? Can you tell me what is n here? What is n here? What should be n here? You can look at the matter wave crest and throw and tell me what is n here. Can someone tell me what is n here? It is consisting of 1, 2, 3 crest, right? So 1 lambda is this, 1 lambda is this, and 1 lambda is this. right? So n will be equal to what? 3 here. So 2 pi r will be equal to what? 3 lambda. The circumference is covered by 3 wavelengths. Okay. Now we are considering that what is the basic nature of the matter waves, right? We are considering here the two probabilities, right? So here if you see that what is the allowed orbit and what is the forbidden orbit in which the particular electron can revolve, right? So here if you see in the first one, n was equal to 3. So this is the allowed orbit. Can you see here? Because there is constructive interference. Constructive interference we have already done before, that what is constructive and what is destructive interference. And also look at one thing, if someone asks you that this particular orbit is allowed or not, look at the matter wave, right? At one position, at one time, or basically at a time, the atom, the electron can be present in a single position only, in a single position only. So here if you see that electron is present here, 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 here at this particular time, right? It can be present anywhere along this matter wave, because matter wave depicts what? Basically the probability of finding the electron, because in a wave you cannot say 100% that an electron is present at a specific point, right? But here if you see what is happening here, if let us say that at this particular point the electron is present at two places, which is not possible, right? In the destructive interference we have already seen that the crest and trough overlap with each other, while in case of constructive interference either crest and crest will overlap with each other, or trough and trough will overlap each other, and henceforth they will increase the amplitude of the resultant wave, right? But here if you see there is a destructive interference. So where there is a destructive interference, that is a forbidden orbit. Why? Because it is stating that at a particular time the electron is present at two positions, which is not possible. Is it clear that what you will classify as the forbidden orbit and what is the allowed orbit? Next we will move on to what is the number of electron waves present on fifth Bohr orbit? What is the number of electron waves present on fifth Bohr orbit? Can you tell me what is the number of electron waves present on fifth Bohr orbit? Answer for this question. See, for the fifth Bohr orbit, if you see, n is equal to 5. So the number of electron waves that are present for the fifth Bohr orbit is basically what? 5. Okay. So number of electron waves is given by the orbit number itself, right? For example, n equals to 2, so number of electron waves will also be equal to 2. If n equals to 3, then number of electron waves will also be equal to 3. If n equals to 4, that is the orbit number equals to 4, then the number of electron waves will also be 4. Okay. Yeah. So de Broglie just gave a hypothesis, right, that the particular matter is associated with some wave nature also, that is known as basically the matter waves, right? So he called his theory as de Broglie theory of the matter waves, right? Now the experimental support basically was given by Davison and Germer experiments on diffraction of electrons through crystal, right? We have studied that what J.J. Thomson did. Yeah, Dipashri, you are correct with the answer. So for J.J. Thomson said that the electron was a particle nature, but on contradictory G.P. Thomson studies suggested that he carried out an experiment basically which showed that electron was having a wave nature, right? So J.J. Thomson, he said that what? That electron was having a particle nature and he proposed his model, while G.P. Thomson said that electron was having a wave nature, right? So now for the practical evidence of the dual nature of electron, more and more experiments were being carried out. It was found out that electrons undergo diffraction as well as they undergo interference also. This was also found out by the experiments which were done with electron, right? So we already know that diffraction and interference explains the wave nature, right? Wave nature of matter. So this from this they concluded that yes, electron is possessing a wave nature as well as the particle nature. So these were the experimental supports which were given to the de Broglie theory of the matter waves. Okay. Now comes the Heisenberg uncertainty principle, right? It states that it is impossible to measure simultaneously both the position and momentum of any microscopic particle. Only for microscopic particles it is there. While in case of de Broglie theory, we did what? That every kind of matter, whether it be a microscopic or a macroscopic particle, microscopic such as electrons, protons, or macroscopic such as the football, marble, right? De Broglie theory explained the concept, explained his theory for both type of particles. But in case of Heisenberg, if you say, his theory was only, or his uncertainty principle was only limited to the microscopic particles, actually the moving microscopic particles, right? So he stated that it is impossible to measure simultaneously both the position and momentum of any microscopic particle, right? So basically, if you see that if we are able to determine the position and momentum of any particle, then we can simply find out the trajectory of that particle. We can simply find out the trajectory of the particle. For example, you must have done the projectile motion, right? So in projectile motion, when you throw a ball or something like this, so the path can be found out, or the trajectory can be found out when the position and momentum can be accurately determined for a particular particle, right? So for big objects, if you see, you can find out the trajectory, right? That how or which path it has followed while moving. But in case of microscopic particles, Heisenberg stated that it is impossible to measure simultaneously both the position as well as the momentum. So if you go on measuring momentum with accuracy, there will be inaccuracy in the measurement of position, while if you are able to measure the position accurately, there will be inaccuracy in measurement of momentum, right? So he said that the uncertainty, that is the inaccuracy in the position multiplied by the inaccuracy or uncertainty in the momentum, is always greater than equal to h by 4 pi, is always greater than equal to this particular value, right? And we have already learned that h by 2 pi can be written as h cross itself. So h by 4 pi can be written as h cross by 2, where h cross is what? Basically h by 2 pi. So he told that the uncertainty, the product of uncertainties of position and momentum will always be greater than equal to h by 4 pi, where h is a Planck's constant with a value of 6.62 into 10 raised to the power minus 34 joule second, right? So what was the basis of Heisenberg uncertainty principle? For example, let us say the de Broglie theory here. He stated that lambda equals to h by t basically, right? And yeah, and one formula we will need here, E equals to hc by lambda. These formulas we know, right? So what he did, For example, let us say that you want to measure a thing, right? Let us say that you want to measure a thing with the help of a scale in centimeters basically, right? So the scale that you will be taking here, let us say, will have centimeters as well as millimeters at unit, right? For example, this is 0, let us say, then this will be 1, this will be 2, this will be 3, and in between you are having the partitions, right? So for example, if I am measuring the length of a certain thing as 1.2 centimeter, right? So basically a smaller unit than that of centimeter is required to accurately measure that thing. Similarly, if you see here that if we want to find out the position basically or the momentum of the electron that is traveling in the orbit, the radiation that we need to provide should be lesser than that of the order of electron, lesser than that of the order of electron, right? So the wavelength should be smaller. Are you able to understand this particular thing? Let me know in the chat section box. Are you able to understand this particular thing? That why was lambda was taken at the lesser than the order of the electron. Okay, good. So here if you see that a radiation was incident on that particular electron and there was a microscope here, right, to basically observe the thing which is happening after the radiation is being incident on that particular electron, right? So what happens is that we know that E equals to hc by lambda basically. So lambda and energy are inversely proportional. So lesser lambda will mean what? Lesser lambda will mean greater energy. Greater energy. This means what? That the radiation that we are taking is of greater energy, right? Now we know that basically the radiation is made up of what? The photons, right? As explained by the Planck's basically, that it is made up of photons. So when photon collides with electron, what happens is that electron absorbs the energy of the photon, right? And because the energy is very much higher, what happens is that when electron absorbs this energy, it there is an increase in the velocity of the electron and it goes out of the orbit simultaneously. So by this kind of thing, that is taking lesser lambda, the wavelength, the wave that is having lesser wavelength and of greater energy, what is happening that electron was gaining much of energy, and because of that more energy, it was expected to follow this path, but because of greater energy it just falls out of its orbit and goes to new path and velocity. So this way you can find out the initial position of the electron but not the path that is followed by the electron, right? This way when lambda was lesser, you can find out position of the electron, what was the initial position, but you cannot find out the path of the electron, right, that it is being followed. If you take lambda at a higher value, this means that of lesser energy, then what will happen? That you can find out the path, but you cannot find out the position of electron. Position of electron. So Heisenberg concluded basically that for particles like electron which are moving continuously in an orbit, if you go to find out the path, you cannot find out the position, and if you are going to find out the position, you cannot find out the path, right? So here if you say that you cannot define momentum and position of an electron, of a moving electron simultaneously. This was the gist of Heisenberg uncertainty principle. Okay. Yeah, so Bohr's model versus Heisenberg uncertainty principle. Now see here that Heisenberg uncertainty principle said that you cannot determine the position and momentum of the electrons simultaneously. If you go on valuing the position accurately, there will be a more uncertainty in momentum. If you will find out the momentum accurately, the position will be inaccurate. Can you see here? If momentum is precise, then position is variable, it is having uncertainty. And if position is, see here, if the position, if you are measuring accurately, what will happen? Momentum will have a variable value and vice versa. So he said that if you do not know the path or the trajectory that is being followed by the electron, how can Bohr say that the electrons are moving in definite orbit, right? So this was the question that was asked by Heisenberg uncertainty principle to Bohr, that if you cannot determine the trajectory of the electron, right, how can you say that what is the position of electron or the distance of electron, or how you can say that electrons are moving in this particular orbit. Okay, so this is a question that Heisenberg's uncertainty principle is applicable for A, moving electrons, B, moving car, C, stationary electrons, or D, cricket ball. What should be the answer for this particular question? After this, we are having one more question and then we will be done with the session. Answer fast. Heisenberg uncertainty principle is applicable for what? Moving electron, moving car, stationary electrons, or cricket ball? A. Arun is saying A, that is moving electron. What about others? Anirudh is also saying A. Dipashri, A. Good. Everyone is correct with your answer. That Heisenberg uncertainty principle has only a significance for moving electrons, right? For microscopic particles which are basically moving, right? It does not explains or it is basically not valid for macroscopic objects and also for stationary microscopic particles. Yeah, you are already you are also correct with your answer. Yeah, so Heisenberg uncertainty principle is not valid for macroscopic object and objects at rest. Rather, it is only applicable for moving microscopic particles. Okay. Now, this is the last question that you have to do, and then we will end up with the session. An electron is confined to a region of width this much, which is its uncertainty in position delta x, right? So this is the delta x. Estimate the minimum uncertainty in its momentum. You have to find out the minimum uncertainty in its momentum. You have to just apply the Heisenberg uncertainty principle. Delta x dot delta p is greater than equal to h by 4 pi. So the minimum uncertainty in the product of position and momentum is equal to what? H by 4 pi, which h is the Planck's constant. So it is talking about the minimum uncertainty. So this will be delta x dot delta p will be equal to h by 4 pi. Delta x value is given, h value you are already knowing, pi take it as 3.14 and find out the value of delta p fast. And after this, Arun, you can ask your questions. What should be the answer for this particular question? Comment down fast. Only you have to put the values. Delta x as 5 into 10 raised to the power minus 11. Delta p you need to find out. H as 6.62 into 10 raised to the power minus 34. Pi as 3.14. Find out the value of delta p. Delta p will be what basically? H upon 4 pi delta x. So this will be 6.62 into 10 raised to the power minus 34 divided by 4 into 3.14 into what is delta x? 5 into 10 raised to the power minus 11. What should be the answer? Okay, Arun is saying 1.09 into 10 raised to the power 44. Okay. Is it minus 44 or plus 44? What about others? Solve it fast and let me know. You just need to calculate this particular thing. Values I have substituted. Just do the calculation part and let me know the answer. Arun, meanwhile you can ask your questions also now. Anyone with the answer? So you will get the answer as 1.06 into 10 raised to the power minus 24 kg meter per second, right? So Arun, your answer was almost correct, but the power was different, that is 10 raised to the power minus 24. Okay. So that's all for today. Thank you. And meanwhile, Arun, you can keep asking your questions. I'll answer them in the chat box. That's all for today. Thank you to all. Happy learning.